In 4.2, we're going to talk about approximating the area under a curve. So given a curve or a portion of a curve, looking at that area that's bounded by the x-axis in the first couple cases, we're also going to look at what happens when the curve goes below the x-axis. So what I want you to do is, for this warm-up, find the area of the rectangles in part A, add them together. For part B, I want you to draw your own circumscribed rectangles, still with a width of 2. And remember, circumscribed meaning that the whole curve is underneath, like the rectangles are completely encompassing the curve. And then for part C, draw rectangles that are inscribed, meaning the rectangles are fully inside the curve. So go ahead, pause the video, draw those rectangles for B and C, approximate the area for all three, A, B, and C, and then answer the question below about whether or not you think that the area you found is actually an overestimate or an underestimate for the area that actually is underneath that curve. All right, for part A, the area of this first rectangle, 2 by 2, the area of this first rectangle is 4. The area of the second rectangle, which is 2 by 5, is 10. The area of the third rectangle, which is 2 by 3, is 6. The area of the fourth rectangle, which is 2 by 1, is 2. The area of the last rectangle from 8 to 10 is 2 by 3, which is 6. And if we add all of these together, we get that the total area is 28. Now, whether or not you think this is an over or underestimate is up to you. I think it's pretty hard to tell. It's probably pretty close to an estimate based on the part that's outside, but I would say it's probably an underestimate, but this is just a guess here. For B, this is what it would look like if we circumscribed the curve, meaning all of our rectangles, the entire curve is encompassed. I think before we even calculate the area here, it's pretty clear that this is an overestimate. Every rectangle is including more area than the curve at that in particular place. So what I'm seeing here is that the area of the red rectangle is 8, the area of the blue one is 10, the area of the purple one is 8, green is 4, and black is 10. So this total area is going to be 40. And then looking at part C, this is obviously an underestimate. There's not a single rectangle that goes all the way over the curve at any point in time. In fact, this whole portion, we're actually saying that the area of that whole portion is 0 based on this strategy. So let's calculate the area here. We have 0 for the red one. We have 8 for the blue one. We have 4 for purple, 2 for green, 4 for black. And if we combine those, we get a total area of 18. So what we just did was we just approximated the area under a curve using rectangles, and that idea is called a Riemann sum. The way that we're looking at it over some closed interval and bounded by the x-axis. At the moment, we're only looking at, since it's bounded by the x-axis, we're looking at the area where y is greater than or equal to 0 over the entire interval. We will actually talk about in this lesson what happens if y goes below the axis as well. But we commonly use geometric shapes to approximate the areas of graphs if we can't find it exactly by hand. If it's a function that we either don't know what the function is or we don't know how to differentiate or integrate with that particular function. The common shapes that you're going to see used for estimating area in this way are rectangles and trapezoids. Also, triangles are pretty commonly used. But when we are using rectangles, that approximation has a special name, and that special name is called a Riemann sum. When you are doing this, what we're doing is we're cutting up the curve into small pieces of length x. Sometimes you are going to be asked to do that with equal pieces, like we just did. The width of all three estimates we just found in A, B, and C had a width of 2. That would be saying we have an equal subinterval, which the way you would find that if you were asked to have an equal subinterval is for B minus A over N. So 10 was the top of this, minus 0, that was the lower limit, divided by, in this case, 5 pieces. That gave us our equal subintervals of 2. You will not always be asked to have equal subintervals. Sometimes you will be specifically told not to have equal subintervals. But if you are asked to have equal subintervals, that's how you find them. The height was whatever the y value was in that particular x region, based on the way that we set up our rectangles. There are a handful of different ways that we could set up those rectangles, and that's what we're going to explore next. So there is a left-handed approach where every rectangle is formed using the left endpoint of the curve. So this would be my height. Each of those purple dots would be the height for each individual rectangle that we would use when calculating the area. Similarly, a right-handed approach means that we're using the right endpoint for each interval of the curve to create the height of our rectangle and calculate the area. And then, similar to what happened on A, we don't know for sure that we use the midpoint, but it sure looks like it on warm-up part A. There is the midpoint approach where you find the intervals that you're using for your width, and then you find the midpoint of those intervals and you use that as the x value to find the height for each individual rectangle. So you would be finding the height using the midpoint of each individual rectangle. So there's left-handed, right-handed, and midpoint. And then there's also the other two that we looked at in part B and C, where we're inscribing each rectangle underneath the curve, but still touching the curve at one point, or where we're circumscribing, meaning we are overestimating and creating the rectangles by bounding the curve above. So below inscribed, we call that the lower sum, and that will always be an underestimate, versus the upper sum, circumscribed, which will always be an overestimate. So what we have done is something that in reality we could have done in middle school. We took some shape or some curve, bounded on both sides, and we said, how do I approximate the area under this? Well, the best way I know to do that is to turn it into shapes that I know how to find the area of. So the idea that should be coming to mind is that we just talked about overestimates and underestimates, but what if we actually want to know the exact area? So Riemann, who came up with these Riemann sums, was asking himself, how do I get not just really close to the actual area, but exactly there? And that should lead us to that question. How do we find the exact area, or how do we get closer to the exact area? And I'm going to show you a really great visual of this in class that I can't pull up when I do notes the way that I am right now. But what Riemann conceptualized was what happens if the rectangles that we're finding the area of and adding together, what happens if I make them smaller and smaller and smaller and smaller? The smaller those rectangles are, the closer they're aligning with the actual curve, which means the closer we're getting to the actual area. How could we make them infinitely smaller? If they were infinitely smaller, which I know is an idea that's sort of weird to wrap your head around, but if they were infinitely smaller, then we're getting exactly to that area. And when we're talking about approaching infinity or making something infinitely small, that leads us to the idea of a limit. And when we have the idea of the limit, taking the limit as we take the sum of all these little tiny rectangles together, as we change the width, that is the idea of a definite integral. And that's where this is actually called a Riemann definite integral. He came up with this symbol and this notation to approximate the area under the curve. And you're going to see in these notes sort of the notation that leads us to this. But right now I just want to talk about how do we use definite integrals and what do they look like. So a definite integral has bounds as opposed to an indefinite integral that had no numbers on it whatsoever. So a definite integral, for example, A, which went from 0 to 10, would be from 0 to 10 of the function that we're talking about, integrated with respect to x. So this dx is really, you can think about that as we're getting infinitely smaller and smaller and smaller and smaller. We're looking at when that rate of change is almost non-existent. It's almost exactly the curve because it's getting infinitely smaller. So this is telling us the area under the curve from 0 to 10. So always from the bottom number to the top number. The area under the curve from 0 to 10 of the function as that width is getting infinitely smaller. So that is the idea of a definite integral. We can integrate from a to b, if that is our interval, of f of x dx. And these two values, a and b, those are called our bounds. So let's look at a few more examples with Riemann sums, with actually approximating it by using those rectangles, and walk through those, and then we'll formalize this idea of a definite integral more. So here we have a curve, the curve negative x squared plus 4 from 0 to 2. So what we're being asked to do here is we're going to evaluate the integral from 0 to 4 of this function. Oh, you can't see my x there. Using 4 different Riemann sums. So we actually have not talked about how do I mathematically do this without having to look at all these graphs and make these rectangles. We are going to talk about that in 4.3. But right now what we're going to do is we're going to approximate that integral using 4 different Riemann sums approximations. So first using right-handed rectangles, second using left-handed rectangles, third using the midpoint rectangle, and 4 using trapezoids. For each of these, we're going to use 4 equal subintervals. So if this goes from 0 to 2, 2 minus 0 divided by 4 intervals, we're going to be using, our width is going to be 1/2 for each of these. And since we have the function, we can actually figure out what each endpoint is without having to approximate it on the graph. So what I want you to do is go ahead, pause this video, draw the rectangles and trapezoids, and then we will go back and actually find each of those ordered pairs to find the area. So let's start with left and right. The right-handed one, you can see I added each of those rectangles. I don't know why there's no straight line tool on this note sharing app that I'm using, but bear with me, pretend that they look like straight lines. So in order to find the area, I need the area of the purple rectangle plus the area of the blue rectangle plus the area of the red rectangle plus the area of the green one, which actually we can already tell the area of the green one is going to be 0 because the height is 0. In order to do that, I need to know what the coordinates are for each of those endpoints on the right. Well, the purple rectangle is existing, or the height is when x is 1/2. So I could use this formula to figure out, okay, what is the y value of that point? So the purple rectangle is going to have area 1/2 times the y value when I plug in 1/2. The y value when I plug in 1/2 is 3.75. The area of the blue rectangle, so I'm going to add these areas together. The width is 1/2. The width for all of them is 1/2. The height is what I get when I plug in 1, right? Because I'm going by 1/2. So the purple one is at 1/2. The blue one is at 1. The red one is at 1.5. The green one is at 2. So if I plug 1 in, I'm just going to get 3. I'm going to add that to the area of the red rectangle, which is 1/2 times the height when I plug in 1.5. which is 1.75, plus the area of the green one, which is 0. And when I add all of those together, I'm going to get that the area is 4.25 units squared. Now, similarly for the left-handed rectangles, the height for the purple one is pretty easy to see. So the width is 1/2, the height is 4. For the blue one, the width is 1/2. The height is the point that we found on the one before, 3.75. Again, you just plugging 1/2 into that function. The red rectangle is width 1 height. Height what I get when I plug in 1, which is 3. And the green one is width 1/2. Height what I get when I plug in 3/2, which is 1.75. And if I multiply all of those out and add them together, I'm going to get 6.25 units squared. Something else I want you to notice, and this is going to seem kind of silly, but obviously if the width is 1/2, I could have written this as 1/2 times 4 plus times the height of each of those rectangles. Since it is the same width each time, this mathematically seems like it would be a lot easier to calculate than actually multiplying 1/2 each time. And those little things save you time when you're working through a problem. So you could add all of the widths together, or add all of the heights together, and then multiply by 1/2 to get your total area as well. Now let's look at midpoint rectangles. So still the width for each of my rectangles is still going to be 1/2, and this time, just to save myself the effort, I am going to just write 1/2, and then I'm going to find all of those heights of each of those rectangles. So the purple rectangle, or the height of the purple rectangle, is going to be what happens when we're halfway between 0 and 1/2. So what happens in the function up top when we plug in 1/4? And when we plug in 1/4, we get 3.9375. The blue rectangle is going to be what we get when we're at x equals 3/4, and that's going to be 3.4375. Not sure if you noticed, but I put the little calculator button on this just for time-saving purposes. The red one, I'm just going to go down here to keep adding. The red one is what we would get at the next midpoint, which is going to be 2.4375. And the green one, when we're at 1.75, that's going to give us 0.9375. And when we add all of those together and multiply them by 1/2, we get that the area is 5.375 units squared. Now, we haven't done a trapezoid area yet, and you should know that the area of a trapezoid is 1/2 times base 1 plus base 2 times the height. So I'm going to go ahead and construct trapezoids with the same width of 1/2, because that's what the directions have asked us to do. Pretend that those look like trapezoids. Actually, the smallest one looks a lot more like a triangle. So let's simplify this a little bit. The area is going to be 1/2 times the height, and the height, so you have to look at these sideways. The height of each of these trapezoids is 1/2. The height of every single trapezoid is 1/2. And it's going to be that 1/2 times the height 1/2 times the sum of the upper base and the lower base, which is basically the left y and the right y of each trapezoid. So for the purple, the left is going up, the left base is 4, the right base is 3.75. For the blue trapezoid, the left base is 3.75 and the right base is 3. For the red one, the right is 3. Sorry, the left is 3 and the right is 1.75. And for the green one, the left is 1.75 and the right is 0. So again, we're saying the left, which is base 1, plus the right, which is base 2. And then we're going to add all of those together and multiply by 1/4. And I'm going to just tell you that the total area here is 5.25 units squared. So there we have 4 different area approximations for the area under the curve of negative x squared plus 4 from 0 to 2. And something to notice, the left and the right-handed ones are drastically different than the midpoint and the trapezoid one, which means that the area is probably somewhere in that 5 range, but we kind of have the upper and lower limit of the lowest. It probably, well, we know that 4.25 is an underestimate and 6.25 is an overestimate, so we can kind of squeeze together what might be an appropriate approximation in between. So that kind of gives you an idea of how to approximate the area under a curve. What I want you to do on example A below this is I actually want you to construct shapes, triangles, rectangles, circles, trapezoids, shapes that you know how to find the area of. I want you to draw them on this picture to approximate the total area under this curve, which we could write as the integral from negative 10 to 10 of f of x dx, the area under the curve from negative 10 to 10. Now keep in mind, if the area is going below the x-axis, that means we're actually talking about negative area. So we would subtract that overall area. So go ahead, break this up into shapes that you think are easy to find the area of and add those areas together, considering that negative area is below the x-axis and positive area is above. So I chose to use triangles for the left 2 pieces. So the negative, the red on my picture has an area of -2. The blue on my picture has a positive area of 8. Then obviously a half circle there, so -1/2 times pi r squared is going to give us -2 pi. And then you could have used a square and a triangle for the other part on the far right, or you could have just used a trapezoid as well. It's going to give you the exact same area. So that's going to give you that purple area is 8. So if we combine each of these things, we're going to get 14 minus 2 pi is the area under this curve. So we could write that as the integral from negative 10 to 10 of f of x dx is 14 minus 2 pi. So the area under the curve from negative 10 to positive 10 of this function is 14 minus 2 pi. So what I'm going to have you do is look at examples 2 and 3 here, or practice problems 2 and 3. Create rectangles the way that you're being asked to do that. Approximate the sum. I'm going to have you pause the video while you do that. I'm just going to fill in the answers. I'm not going to walk through them step by step. And then we're going to wrap up by talking about how to improve that approximation and really what I kind of referenced earlier about Riemann's definite integral. So on 2, 0 to 6 with 3 equal subintervals, just as a reminder, that means that each of your rectangles are going to have a base of 2. And then it asks you to do midpoint on A right-handed and on B left-handed. Also notice on A and B you're going to use 4 subdivisions instead of 3. So just keep those things in mind while you're working on this. So here now you have 2 and 3 all the way worked out. Pause the video, check over and make sure you got these. Make sure that on A and B you're subtracting negative area. And remember that I am finding these heights from plugging these values into the functions that they gave me based on the endpoint that I'm using to find the height. So as I mentioned, the last thing that we're going to do is really slightly more formalize the Riemann integral based on the idea behind how he came up with this. So the simplest way to improve an approximation is to have smaller and smaller rectangles, right? So we want that delta x, we want the width to be getting infinitely smaller, and that width is represented right here. Delta x equals b minus a over n. And that's what representing the width of our rectangle. The height of our rectangle is what we get when we evaluate at that given point. So we're going to let this f of c sub I, we're going to have that be our height. So how do we find the area? We multiply our width times our height. And we add all of those widths times our heights together. That's how we come up with the overall area using a Riemann sum. But if we want this to get, if we want each of these rectangles to get closer and closer and closer to actually representing the curve, what we need to do is we need to take the limit as the subintervals are getting closer together. So the limit as n approaches infinity. That means we're getting infinitely smaller with our rectangles getting closer and closer and closer to the curve. And that's where this idea came from for the definite integral. So the integral from a to b of f of x dx. And what that means is the area under the curve starting at a and ending at b of that function while we're having those rectangles get infinitely smaller and smaller and smaller. That's where this integral came from. Something else in here, and you might see this notation used on a variety of different types of AP style questions. This is really just saying the height of each rectangle, and it's because we're talking about A being our starting point and delta x is the same thing as saying b minus a times I. I is just whatever we're changing by over n. So this notation, f of a plus I delta x, is saying the first endpoint, then the second endpoint, then the third endpoint, as we're moving further to the right, evaluating our functions, whether we're using a right, left, any kind of Riemann sum. So this is representing the starting point, wherever the interval we're integrating over starts at, a, plus the change in the height, change in the width to find the height. So to wrap up this lesson, the big ideas that are happening here, we're talking about approximating the area under the curve using a Riemann sum, looking at different styles of rectangles, whether they're left-handed, right-handed, midpoint constructed rectangles, whether we're looking at inscribed or circumscribed rectangles, evaluating or estimating an area under a curve using that idea. That idea leads into the idea of a definite integral, an integral that has an upper and a lower bound that we're going to evaluate it over, which gives us the ability to say, as we make the width of those rectangles smaller and smaller and smaller, infinitely smaller, and we look at those sums, what we can do is have an integral that we can evaluate. And what we're going to do in 4.3 is we're going to talk about how do we evaluate this without actually having to draw a graph and look at these rectangles. How do we evaluate this mathematically, algebraically, as opposed to in a more analytical graphic sense? So that's what you have to look forward in 4.3, and I look forward to working with you in class on this. Thanks for listening.